Yeah, so this week we have Alan Mair talking about effects of drought and climate change. To introduce Alan, he's a hydrologist with the U.S. Geological Survey's Pacific Islands Water Science Center. His research focuses on quantifying the effects of climate and land cover change on water resources in Hawaii. And he received his PhD in natural resources and environmental management from the University of Hawaii at Manoa before joining USGS. And he completed a postdoctoral fellowship at Manoa with the Water Resources Research Center and Department of Earth Sciences, formerly Geology and Geophysics. So with that, I'll let you take it away.
Okay, thank you, Carrie. Aloha, everyone. On behalf of my colleagues, including Delwyn Oki, Heather Kane, Adam Johnson, and Koyo Rotsal, thank you for the opportunity to share results from a study that's aimed at quantifying the potential effects of drought and cloudwater interception on groundwater recharge and wildfire risk on 5 of the main Hawaiian Islands, including Kauai, Oahu, Moloka, Maui, and Hawaii. So over the last year, we have shared elements of this study in other forums, but today's talk marks the first opportunity to share a more comprehensive summary of our preliminary findings. So support for the study was provided by the USGS Pacific Islands Climate Adaptation Science Center. Okay, the main objective of this study is to provide information for assessing the effects of drought on wildfire risk and groundwater recharge for recent and future climate conditions. We also were aiming to evaluate the capacity of cloudwater interception to mitigate the hydrologic effects of drought. And what I mean by that is the negative effects on groundwater recharge and negative effects on wildfire risk. So assessing the effects of groundwater recharge and wildfire risk, 2 distinct subjects into one talk, may appear odd, but the link between them boils down to soil moisture. So in this study, we use a modeling approach that simulates changes in moisture, soil moisture, in the plant root zone for different climate and land cover conditions. The approach tracks changes in soil moisture to estimate from the plant root zone, which we call groundwater recharge. The changes in soil moisture are also used as an indicator of moisture stress in vegetation, landscape flammability, and ultimately wildfire risk. So I've divided the talk into 3 sections. First, I'll provide some background information on wildfires and drought here in Hawaii, and the use of soil moisture to help identify areas at risk for wildfire. Next, I'll describe our approach to estimate groundwater recharge and assess moisture stress for a set of drought and land cover conditions. I'll then present some preliminary results in 2 parts. The first part will describe results for addressing groundwater recharge effects, and the second describes the potential effects on wildfire risk. So beginning with some background, in 2015, Clay Trauernicht and others examined the frequency, extent, and long-term trends of wildfires in the Hawaiian Islands over a 110-year period. And they found that the annual area burned has increased dramatically since the early 1900s. They also noted that land cover within the perimeters of these wildfires was dominated by non-native grasslands and shrublands. They further noted that during the period, a 7-year period from 2005 to 2011, the mean annual area burned statewide as a fraction of total land area was greater than in the 12 states in the wildfire-prone Western US. This suggests that wildfire risk in Hawaii is among the highest in the nation. And they concluded that additional tools and information are needed to better assess wildfire risk at landscape scales. In a more recent publication, Abby Fraser and others reported that drought frequency and intensity has increased across Hawaii over a 100-year period. They used a data set of drought index maps to identify the worst droughts in the Hawaiian Islands. Shown here are the 2 worst statewide droughts. a 5-year drought from 1998 to 2002, shown in the lower right, and an 8-year drought from 2007 to 2014, shown in the upper right. They ranked the 2007 to 2014 drought as the worst drought for Hawaii Island, and the 1998 to 2002 drought as the worst drought for the rest of the islands. The wildfire science community knows that the moisture content of live and dead vegetation, collectively referred to as fuel moisture content, is an important characteristic for assessing wildfire risk because it can influence wildfire propagation. So when fuel moisture content is high, wildfires are more difficult to ignite and tend to burn poorly because more energy is needed to evaporate water. But when fuel moisture content is low, wildfires tend to start easily and can rapidly spread and intensify. So estimates of soil moisture can be a useful surrogate for estimates of live fuel moisture because soil moisture is linked to the physical interactions between soils and plants. So in the Hawaiian Islands, estimates of soil moisture and fuel moisture have been used to assess wildfire risk and behavior. A study by Klaus Doling and others, shown on the left, found a strong link between the Keach-Byram Drought Index, an index that conceptually describes the soil moisture deficit, and the total area burned over a 20-year period on the islands of Oahu, Maui, and Hawaii. Later in a study by the center, found a close correlation between fuel moisture and soil moisture and other meteorological variables at multiple monitoring sites in West Oahu. Their model simulations in these areas indicated that wildfire spreads 3 to 5 times more rapidly in grassland than forest. And then finally, remotely sensed estimates of soil moisture, with an example shown on the far right, have also linked soil moisture to wildfires in continental settings such as California and Australia. Evapotranspiration and climatic water deficit have also been used in wildfire danger assessments in other parts of the US. And in this study, climatic water deficit was defined as the evaporative demand that exceeds available water. The approach of this study involved applying a water budget model for a set of climate and land cover conditions. We established a reference condition for rainfall and land cover. We also have a historical drought rainfall condition, a future drought and non-drought rainfall condition, and then a land cover scenarios that involve hypothetical deforestation within the cloud zone. So the hypothetical deforestation was used in the study to assess the effects of reducing or eliminating cloud water interception on groundwater recharge and wildfire risk. So for part 1, which we addressed groundwater recharge, and in that we quantify the changes from our reference conditions. And in part 2, we'll look at wildfire risk, where we will quantify the changes from our reference conditions in terms of frequency characteristics for soil moisture, ET, and climatic water deficit. So how do we estimate recharge and other water budget components? Well, our center has developed computer codes to estimate regional groundwater recharge and other water budget components using a water budget model approach for estimating the effects of land cover and climate change. This method requires input data that quantify the spatial and temporal distribution of water budget components such as rain, land cover, soils, runoff, and reference ET. It can also incorporate inputs of cloud water interception, irrigation, and seepage from sources such as wetland taro, reservoirs, and septic systems. We use the water budget accounting for tropical regions model, or WaterMod code, to estimate recharge, soil moisture, ET, and climatic water deficit. The code was published earlier this year by my colleague Delwyn Oki. However, earlier versions of the code have been used to estimate recharge in Hawaii, Guam, and the Marshall Islands. In a recent companion study, WaterMod was also used to estimate mean annual recharge on 6 islands for recent and future climate conditions and 2020 land cover. We used the estimates of mean annual recharge for 1978 to 2007 rainfall and 2020 land cover from that study, just shown on the left of this hand of the slide, as the reference condition for comparing recharge estimates from this study. We used the gridded monthly maps of rainfall during 1920 to 2012 from Abby Fraser and others to identify 5 and 6 year periods with the lowest mean annual rainfall. We used those results and the drought analysis of Abby Fraser to select a historical drought condition for each island. We selected the 1998 to 2002 drought for the islands of Kauai, Oahu, and Moloka, and the 2007 to 2012 drought for the islands of Maui and Hawaii. We then defined 2 sets of rainfall conditions for the water budget model simulations. The first set of rainfall conditions was used for part 1 to estimate the effects of historical and future drought on groundwater recharge. The second set of rainfall conditions was used for part 2 to estimate the effects of historical and future drought on soil moisture, ET, and climatic water deficit. Future drought rainfall conditions for both parts 1 and 2 were developed by adjusting historical drought rainfall conditions for a future dry climate projection. Shown here are end of century mean annual rainfall anomalies for one warming scenario, the RCP 8.5 scenario, developed using each of 2 downscaling approaches. On the left are the anomalies developed using a statistical downscaling approach, which projects extensive drying across the 5 islands and some wetting along the northeast coasts of Maui and Hawaii Island. On the right are the anomalies developed using a dynamical down approach, which shows drying as well as extensive wetting across each of the 5 islands. For this study, we selected the RCP 8.5 2071 to 99 projection from Oliver, Tim, and others, just shown on the left, as our future dry climate condition. However, over the last 2 years, additional downscaled climate data sets have been published, and these include projections by Shui and others, Fandrich and others, Portini and others, and Mizukami and others. However, at the time we initiated this study, these projections weren't yet available. A set of 3 land cover conditions were developed for the study, including a reference condition consisting of land cover around 2020. The effect of reducing or eliminating cloud water interception was evaluated by converting forest and shrubland land cover within the cloud zone to grassland, for which cloud water interception was considered negligible. 2 hypothetical deforestation land cover conditions were defined to simulate the hydrologic effects of the loss of cloud water interception. The first was a land cover condition in which roughly 50% of shrubland and forest areas within the cloud zone were converted to grassland. The second was a land cover condition in which 100% of shrubland and forest areas within the cloud zone were converted to grassland. In this study, the hydrologic effects of the loss of cloud water interception during drought were evaluated for only Oahu, Maui, and Hawaii Island. Oahu was selected because of the high utilization of groundwater resources. Maui and Hawaii Island were selected because they have large areas within the cloud zone. The 2020 land cover maps, our reference condition, was developed by our companion study for use in water budget model simulations. The maps identified 28 types of land cover and were generated by modifying a USGS landfire map with existing vegetation. The cloud zone was delineated using available information from field studies on each of the islands. The base of the cloud zone was delineated at 2,000 feet on Kauai, Oahu, and Moloka, and windward parts of Maui and Hawaii Island. And these areas are outlined in black in the maps you see. For leeward parts of Maui and Hawaii Island, the base of the cloud zone was delineated at 2,600 feet. And that's outlined in red in the maps for Maui and Hawaii Island. These maps highlight the changes for each of the 2 deforestation conditions. The left half of the slide shows the change from 2020 land cover to deforestation 1 land cover conditions, where roughly 50% of the shrubland and forest areas within the cloud zone were converted to grassland. The right half of the slide shows the change from 2020 land cover to deforestation 2 land cover conditions, where 100% of the shrubland and forest areas within the cloud zone were converted to grassland. And these areas are indicated, the changes indicated by the pale green or pale yellow color. Okay, moving on to results. We're going to start with part one, addressing groundwater recharge. So we developed a set of 13 water budget scenarios to estimate the effects of drought and the loss of cloud water interception on recharge. Each presents a unique combination of rainfall land cover conditions. A scenario consisting of 1978 to 2007 rainfall and 2020 land cover was used as the reference condition for all comparisons. The historical drought 1 and future drought 1 scenarios, shown in shades of orange, were used to estimate the effects of historical and future drought on recharge for Kauai, Oahu, and Moloka. And the historical drought 2 and future drought 2 scenarios, shown in shades of yellow, were used for Maui and Hawaii Island. For Oahu and Maui and Hawaii Island, each drought condition was combined with the two hypothetical deforestation land cover conditions to estimate the hydrologic effects of reducing or eliminating cloud water interception on groundwater recharge. Shown here is a map of estimated changes in aquifer system recharge for historical and future drought conditions on Kauai and Moloka. The shading indicates greater intensity or greater reduction. So pale yellow indicates a reduction of up between 10 and 20%, whereas the dark red indicates reductions of over 90%. The greatest decreases in aquifer system recharge occur in the leeward parts of each island, as you can see by the darker reds, oranges and reds indicated in these for both Kauai and Moloka. Shown here is a map of estimated changes in aquifer system recharge on Oahu for historical and future drought conditions, shown by column across the top, labeled across the top, and 3 land cover conditions, which are shown on the shown by row. For 2020 land cover conditions, which is the first row, the greatest decreases in aquifer system recharge occur in the leeward part of the island for both historical and future drought conditions. Deforestation does have a negative effect on recharge because the conversion of forest and shrubland to grassland in the water budget simulations effectively eliminates inputs of cloud water interception. However, the effect on on aquifer system recharge is noticeable in only a few aquifer systems here in this slide. Shown here is a map from Maui. And for 2020 land cover conditions, the greatest decreases in recharge for both historical and future drought conditions occur in selected systems of leeward Maui. The negative effect of deforestation on aquifer system recharge is noticeable in this slide in several aquifer systems in both east and west Maui. These are aquifer systems with large areas within the cloud zone. Finally, on Hawaii Island, the greatest decreases in recharge for historical and future drought conditions and 2020 land cover occur in aquifer systems of leeward Hawaii. Again, the negative effect, similar to the other islands, the negative effect of deforestation on aquifer system recharge is noticeable in the aquifer systems in both east and west Hawaii, where there are large areas within the cloud zone. Shown here is a plot of estimated changes in island-wide recharge for each of the five islands plotted along the y-axis, the x-axis, and values for the island-wide anomaly plotted along the y-axis. So historical drought conditions, which are indicated in pale orange and pale yellow, correspond to a decrease in island-wide mean annual recharge of between 30 and 39% across the five islands. And this translates into decreases ranging from 83 million gallons per day on Moloka to about 2,700 million gallons per day on Hawaii Island. Future drought conditions, as indicated in the darker orange and darker yellow colors, correspond to a decrease in island-wide recharge ranging from between 40 and 51%. And those translate to decreases ranging from 116 million gallons per day on Moloka to about 3,200 million gallons per day on Hawaii Island. Shown here is a plot of estimated changes in island-wide recharge for scenarios that include the effect of deforestation on the islands of Oahu, Maui, and Hawaii. On each island, the conversion of forests and shrubland areas within the cloud zone to grassland further decreases island-wide recharge for both historical and future drought conditions. So for example, on Oahu, which is shown in the far left in orange, complete conversion of forests and shrubland areas within the cloud zone correspond to land cover-related decreases in island-wide mean annual recharge ranging from 10 to 12 million gallons per day. So if you look at the far left, the first three bars, the first bar, the pale yellow, represents 2020 land cover for historical drought. And then the third bar, third from the left, represents deforestation to or complete conversion. And that change between the first and third bar result in about a decrease of 12 million gallons per day. For Maui, complete conversion of forest and shrubland areas to grassland within the cloud zone corresponds to decreases in island-wide mean annual recharge ranging from 119 to 135 million gallons per day. And finally, on Hawaii Island, shown on the far right, conversion of forest and shrubland to grassland corresponds to land cover-related decreases ranging from 690 to 850 million gallons per day. Okay, now moving on to part two, where we address wildfire risk. For the wildfire risk component, we developed a set of 10 water budget scenarios developed to estimate the effects of drought and reducing or eliminating cloud water interception on soil moisture, ET, and climatic water deficit. Each scenario represents a unique combination of rainfall and land cover conditions. We used a 23-year simulation period during 1990 to 2012 in the water budget analysis because this corresponds to the period of overlapping data sets of monthly rainfall from Abby Fraser and others and daily rainfall from Ryan Longman and others. The 1990 to 2012 simulation period was then divided into a drought and non-drought period. The non-drought period consisting of 1990 to 97 and 2003 to 2006 rainfall and 2020 land cover was used as the reference condition for all comparison. The scenarios for historical drought are shown in shades of orange, while the scenarios for future non-drought are shown in shades of gray and blue, and the scenarios for future drought are shown in shades of gold. Okay, this chart describes the process we use to assess whether there were significant differences in the estimates of soil moisture, ET, and climatic water deficit between drought and non-drought periods. The purpose of these analyses was to determine whether estimates of these indicators within the perimeters of wildfires changed significantly. We then compared the indicator values from the reference condition to the values for each of our three rainfall conditions. That is our historical drought, our future non-drought, and our future drought condition. For these analyses, we used a geospatial data set of wildfire perimeters during 1999 to 2019 that were provided by Clay Trauernicht. We selected a subset of 187 wildfire perimeters during 1999 to 2012 to overlap with the simulation period from 1990 to 2012. Land cover within each of the 187 wildfire perimeters is highlighted in this map. Land cover within most of the wildfire perimeters is dominated by grassland, which occupies about 63% of the areas you see, which is shown in pale yellow. Grassland is shown in pale yellow. And most of these wildfires tend to occur in the drier leeward parts of each island. In terms of total area burned, expressed as a fraction of island area, Moloka had the highest fraction of area burned during this 14-year period. Shown here are plots of the distribution of area-weighted mean values of soil moisture, ET, and climatic water deficit within each of the 187 wildfires, plotted along the y-axis of each box plot, and for 5 different rainfall conditions plotted along the x-axis of each box plot. The 5 rainfall conditions include the month of the wildfire, historical non-drought, which is our reference condition, and historical drought, future non-drought, and future drought conditions. We found statistically significant differences in estimates of soil moisture, ET, and climatic water deficit between each rainfall condition and our reference condition. These results indicate that low moisture conditions, which characterize the majority of wildfires during the 1999 to 2012 time period, occur with more frequency during drought or a drying climate. Increases in the frequency of low moisture conditions imply lower fuel moisture, greater landscape flammability, and ultimately increased wildfire risk. Value of area-weighted median value of area-weighted mean values during the month of occurrence of each wildfire as a threshold for each indicator, as shown in red on each box plot. So for example, the value of 0.074 was selected as the threshold for soil moisture with a box plot in the upper left. And the threshold values were then used in a frequency analysis of monthly time series data produced by the water budget model to identify areas of increased moisture stress and wildfire risk. Shown here is a map of the relative frequency of monthly mean soil moisture less than or equal to a threshold value of 0.074 for a reference condition. Areas of blue indicate a low relative frequency and suggest relatively low moisture stress. Areas of green, yellow, and orange and red indicate increasing relative frequency and suggest higher moisture stress, which implies low fuel moisture and increased flammability. Areas of low moisture stress extend across many of the wet, mountainous, and windward areas of each island, whereas areas of high moisture stress occur mostly in the drier, leeward, low elevation areas, except for the drier summit areas of Haleakala on Maui and Mauna Kea and Mauna Loa on Hawaii Island. We've also overlaid, maybe difficult to see, but we've also overlaid the perimeters of the wildfires here. So you can see that many of the wildfires do occur in the drier parts of the island, but some do occur. For instance, the wildfires occurring around Mauna Kea and around Mauna Loa do occur in areas with no moisture stress, but many of those fires occurred during a drought period. Shown here is a map of the relative frequency of monthly evapotranspiration less than or equal to our threshold value of 0.96 inches. Areas of low moisture stress extend across many of the wet and mountainous and windward areas. And again, high moisture stress occurs mostly in the dry, leeward, and low elevation areas, except for the summit areas of Maui and Hawaii Island. And shown here is a map of the relative frequency of monthly climatic water deficit, greater than or equal to our threshold value of 0.77. And so like soil moisture and ET, areas of low moisture stress extend across many of the wet, mountainous, and windward areas of the island, whereas areas of high stress, moisture stress occur in the drier, leeward, low elevation areas. Again, except for the summit areas of Maui and Hawaii Island. So to identify where changes in the frequency of low moisture conditions are greatest, we computed the difference in relative frequencies between our 3 rainfall conditions and our rainfall condition. However, due to time limitations, I will only be describing changes in relative frequency for soil moisture. In this map, we show the change in relative frequency of low moisture conditions for 3 scenarios for Kauai and Moloka. Areas in gray indicate essentially no change in frequency and tend to occur in the wet mountainous areas and the irrigated areas of each island. Areas of green, yellow, orange, and red indicate increases in frequency, which imply longer durations of high moisture stress and greater potential wildfire risk. The greatest increases in wildfire risk correspond to areas where the changes in frequency are large, and those include areas that are shaded in yellow, orange, or red. This map shows the change in frequency for Oahu. Changes according to land cover condition are arranged by column, whereas changes according to rainfall condition are arranged by row. Areas with little to no change in frequency again occur in the wet and mountainous areas or in irrigated areas of Oahu. For 2020 land cover conditions, which are shown in the first column, increases in frequency occur across extensive lowland and leeward areas. Increases in frequency are greatest for leeward parts of Oahu, particularly for the future drought condition, which is shown in the bottom row. The extent of unaffected areas, that is areas that are gray, noticeably contracts during the future drought rainfall condition, which suggests an expansion of increased wildfire risk in upland areas. Conversions of forest and shrubland areas within the cloud zone to grassland further increases the frequency of low soil moisture conditions for each rainfall condition, particularly in the area around Mount Kaua. This is maybe evident, well, it's tough to see, but in the bottom row, where we move from 2020 land cover to the deforestation 2 land cover around Mount Kaua, we change from an area of gray, which indicates no change in moisture stress, to blues and greens, which indicate an increase in low moisture conditions and thereby an increase in wildfire risk. This map shows the change in frequency for Maui. As before, areas with little or no change in frequency occur in the wet mountainous areas, West Maui and windward Haleakala, and in irrigated areas of Maui. For 2020 land cover conditions, increases in frequency across extensive lowland and leeward areas. And the greatest increases are indicated for the leeward part of West Maui and southwest Haleakala. The extent of unaffected areas noticeably contracts during the future drought rainfall condition, which suggests, similar to Oahu, an expansion of increased wildfire risk in upland areas. Conversions of forest and shrubland areas within the cloud zone to grassland further increases the frequency of low soil moisture conditions, particularly in the leeward upland areas of West Maui Mountain and Haleakala. And these are indicated by the changes to the yellow and red, particularly in areas where we had areas that indicated no change. For instance, the 2020 land cover and future drought scenario shown in the bottom left. As you move from left to right, you see how the area of no change contracts around West Maui Mountain. This map shows the change in frequency for Hawaii Island. Areas, as with Maui, areas with little to no change in frequency occur in the wet windward areas and in the upland areas of South and West Hawaii. For a 2020 land cover condition, increases in frequency occur across extensive areas of Hawaii Island. And these increases are greatest across Northwest and South Hawaii Island, particularly during the future drought condition or driest condition. The extent of unaffected areas noticeably contracts too during the future drought rainfall condition, which also suggests that the increased wildfire risk in many upland areas. And then finally, the conversions of forest and shrubland areas within the cloud zone to grassland land cover further increases the frequency of low soil moisture conditions, particularly in the upland areas of West and South Hawaii. So to summarize, starting with part 1, which addressed groundwater recharge, we noted that absolute changes in recharge were greatest in wetter, windward areas, whereas relative changes were greatest in drier leeward areas. Island-wide estimates of recharge decreased for both historical and future drought conditions, ranging from 30 to 39% for historical drought and 40 to 51% for future drought. And then finally, we found that the loss of cloud runoff interception through land cover conversions correspond to substantial land cover related decreases in groundwater recharge estimates. These range from 10 to 12 million gallons per day on Oahu, 119 and 135 million gallons per day on Maui, and 690 to 850 million gallons per day on Hawaii Island. And for part two, that addressed wildfire risk, we did find that estimates ET and climatic water deficit within the perimeters of the wildfires do show significant differences between the different drought and non-drought periods for both recent and future climate conditions. That helped us to establish frequency maps that provide information for identifying areas of potential increased moisture stress and wildfire risk. And then finally, that increases in wildfire risk, we found that increases in wildfires during the projected future drought are greatest in leeward areas and tend to occur in mid to high elevation areas. And with that, I will say thank you. A big mahalo to the USGS Pacific Islands Climate Adaptation Science Center for their funding support, and thank you for your attention.
I'm going to open it up to questions, starting with the live audience.
Great talk, Dave. Thank you. I'm not up on the latest with regard to the lifting condensation layer. I think the modeling assumes that that stays the same throughout all your conditions. Is that a valid assumption? What do we know about the base of condensation?
That's a good question. The projection, first off, the projection we chose was a statistical downscaling projection, only looked at rainfall. So we looked at changes in rainfall. We have looked at that with the dynamical downscaling projections. The data set that we considered, we don't have information on how that changes. We have the projections, but how it's interpreted and how that affects the lifting condensation level or the trade wind inversion, it's not clear yet. So I don't have a good answer for you. So we just assume no change.
I thought at one point a few years ago that there were observations that the condensation layer was migrating to higher elevations on the Big Island. Is that,
well,
are there observations to that effect?
We used observations over that have been collected in field studies, which actually ended up with us revising the cloud zone. We actually ended up lowering it based on the windward side of Maui or windward side of Hawaii Island from previous studies. And we ended up raising it on the leeward side. We went from 2,000 feet in our prior studies to 2,600 feet in these studies for both Maui and Hawaii Island. And a lot of that's just based on empirical evidence that we have. But if there's information that we can use, we would definitely readily try to incorporate that.
The trade wind inversion observations. Also.
Yeah, in that case too, we used, we revised that as well. We used that based on sound measurements by Shinshui Zhang. Looked at some changes, and I think we lowered our trade wind inversion height for this as well, for this analysis. Although I didn't reflect that there, but it ended up kind of pinching it, especially in Maui. Ended up actually contracting the cloud zone.
Thank you.
Yeah.
On lifting condensation level, I just would like to refer folks to a paper by Aurora Kagawa-Viviani that analyzed temperature change and found that the cloud zone, unlike the areas above and below, down at sea level, for example, was not significantly warming, and traced that to basically changes in the lifting condensation level that were inferred by that. And so that implied drying in the boundary layer, and having to lift for to a greater elevation to reach the lifting condensation level. So I would refer you to that. But I think all the evidence except until that time for Hawaii suggested there would not be much change in the lifting condensation level. That basically the increasing air temperature is accompanied by increasing water vapor content, so that the relative humidity of the boundary layer stays about the same. And so even at higher temperatures, if the relative humidity stays the same, the lifting condensation level only changes by a few meters. It's not significant. But so I think, you know, observations, there are some observations suggesting that it has been an increase in lifting condensation level.
Can I? So,
Oh,
yeah.
I didn't know you were there.
caveat that,
Sorry.
though? That was based on like about 2 decades of ceilometer and sounding data. So it is not, you know, we only had a short period of data, and it doesn't speak to what's actually contacting the land surface, right? So these are like Hilo Airport, you know, atmospheric measurements. So that's, I mean, I think it's still kind of a really good question. I have a question about soil moisture. I apologize if I missed it, but how did you calculate soil moisture? And specifically, I'm thinking about like the vegetation implications on like Hawaii Island, where soil is, I mean, well, one, it's pretty unmeasurable to measure soil moisture in awe. Like, how did you approach that soil moisture index?
Well, we used a regional map from the National Natural Resources Conservation Service. So that's what we use as our reference for establishing soil moisture. And then we looked at we end up looking at the different depths of soil moisture as it changes across the landscape. So I think and then we assign, available water capacity based on that. I think we had to assume at least some water capacity in even lava rock, because we've observed there is vegetation there. So for this purpose of this modeling, we had to assume some minimal level of available water content or available water capacity. So when I'm describing soil moisture here, it's all computed as a fraction of available water capacity, which is information we gathered from the NRCS maps.
Alan, so your premise here is to look ahead and expect deforestation to occur. Is there any justification for that?
The purpose of this was, our objective was to basically quantify the importance of climate change. And we did that by saying, hypothetically, what if we took forest away? What if we took shrubland away? What would that affect? And it also tied into the importance of watershed conservation. So why are we preserving our forests? So if we took allow those forests to convert it could be through wildfire or other mechanisms, what would the impact to water resources be?
Yeah, I guess I would suggest maybe for the next round of this study, maybe for future round of this study, that you look at afforestation, because that is probably more likely in these vast areas of pasture on Big Island and Maui that are in the cloud zone and that are becoming less, I'm told, less economically viable for ranching over time, and so that they're looking for alternatives, including afforestation for various purposes, for conservation, water conservation, and for high value timber and so forth. And also look at, it may be a lot more difficult to tease out the differences, but looking at the effects of non-native tree invasion into the forest, and they have different structural characteristics and might affect the cloudwater interception.
Yeah, in our study, we had to generalize some of the land covers, so we don't necessarily distinguish between different types. It's in forests, we have basically 2 conditions: non-native forest as well as native forest. However, in this study and in the prior study that we did incorporate Kiawe as we have a specific land cover now for Kiawe, and so we were able to now simulate, for example, ET in Kiawe across the landscape, as well as because it's a phreatophyte, we can estimate how much groundwater it's actually sucking up in coastal margin areas. And that's due to research from Yoshi Miyazawa and Bruce Studley, they did in Kihola. So if we have studies like that information and we can incorporate that, yes, we would do that.
Okay, any more questions from the live audience? So far, we don't have any chat questions, so.
right, if there's,
I'm for one. We have time. So, this is great, Alan. Like, what's the next project besides the one Tom suggested?
The next project, well, there's a whole new, there's a whole new set of climate projections that I haven't looked at. So, yeah, I'm curious to see how these compare with our past. We've been relying on two general sets of climate projections, and now we have 4 more. So I'm curious to see how those compare. So that would be one. But I'm welcome to considering doing the afforestation, going the other direction and seeing how we could increase water supply through cloudwater interception in these environments.
Basically, I've been struggling with the fundamental difference. Like, recharge happens in these episodic moments, but ET happens over the longer time periods. And so how do we think about recharge when when our rainfall regimes, not just like monthly or annual volumes are changing, but they are more episodic. They might partition differently at the land surface. Have you guys given thought into how you're gonna kind of dial into some of those finer mechanisms?
Well, we base, the way we treat that, it's that we run the water budget model in these in our prior studies. We already run it at a daily time step. So all our values are input at a daily, from daily values. And so, we use what's available. And in this case, we used Ryan Longman's 25-year daily rainfall data set from 1990 to 2014. I will say we've looked at that and how that differences between the way we used to do it, looking at specific gauges and how the daily rainfall frequency for an area based on one rain gauge versus Ryan's grid data, and we did see some differences there. So we actually saw greater ET with Ryan's data set, which seemed to indicate there was more diffuse rainfall curling at a daily frequency across the landscape, which then enhanced wet canopy evaporation and ended up decreasing recharge. So there was some of that going on, which explains why we had to discuss, or we do discuss, why we saw some declines in recharge, and some of it's based on these changes in daily rainfall or the inputs for our daily rainfall.
Are there models of, I'm sure there are, aquifer sustainability, and do they take into account recharge? They must. And are your recharge findings going to be folded into aquifer sustainability studies?
The answer to the first part is yes. Yeah, our center does use numerical groundwater models to look at changes to water levels and salinity. Are there specific plans to incorporate this information like from this study? I'm not aware of any yet.
What do you currently use for future recharge?
We, depending on the scenario, sometimes, and then depending on the objectives of the study, if they're looking at over the long term, we may use a mean annual recharge, which I showed earlier in the slide was that 30-year period that the 78 to 2007. We might look at the average recharge over that entire period. In some cases, they have looked at how recharge varies over shorter time periods, like a 5-year drought. So it kind of depends on the objective. But I've seen them do it both ways.
Are your results a better?
Well, we continue to refine the water budget. Recharge is the one thing it's very difficult to measure in the field. So the better information we have on the other inputs like rainfall, ET, and runoff, the more confidence we have in recharge. But there's still a lot of question marks. We still we need more information. As Tom alluded to, impacts from non-native plants and how that alters the landscape in terms of ET. Yeah.
Yeah, one of the things that you did address, and I would like to see the details, delve into details a little more, but it is a big question, I think, about reforesting pasture lands, and that is in the cloud zone. So the question is, do you gain more from cloudwater interception than you lose from increased evapotranspiration? So do you have an answer to that from your study?
Well, based on what we saw here, it looks like when we changed to grassland, we saw a decrease. Yeah.
So do you see much spatial variability within the cloud zone on that?
I don't know the answer to that. I'd have to look. I don't know the answer to that. Sorry. Yeah. You could look at the aquifer system change, but looking in the maps here, it just tells you the kind of indicative of the amount of area they have, the footprint that's within the cloud zone. But actually, if you're looking on the maps, I'd have to take a closer look at that. I don't have a straight answer for you right now.
Okay.
Sorry.
I have some more
One
comments.
more. Thanks, Ellen. So going off of Tom's suggestion of looking at different vegetation compositions and assemblages, what parameters do you need from field experiments to plug into your model to answer that question? Like KFS, like what do you need?
That's a great question. And we actually have a separate study that is looking on that. And that kind of evolved out of the collaborative study that we did with UH on ecohydrology. And that is a study that is looking at what are the field parameters of most importance in different environments. So say leeward versus wet areas on the different islands. So that is a work in progress. So that's something that we've considered. Yep.
So how well do you think your model is able to simulate cloudwater interception and the spatial variations in cloudwater interception and temporal variations with changes in conditions?
A lot of what we do is calibrated to empirical data. So we calibrate it towards, studies that have been done in the past. And each island sometimes is treated a little differently. So we don't have a uniform approach, in other words, for each island. And that's based on the availability of data. So I understand that at some point there may be a cloudwater interception map statewide. And that would be something that we'd hope to use to answer that question. Yeah.
I'll just add that the existing vegetation type for Hawaii has been updated. And so there will be additional vegetation types that we can look at, but it wasn't completed at the time we did the study. So for future studies, that was one thing we would want to use and improve upon the land cover maps. And, they did have specific native and non-native vegetation type for Hawaii. I think it's increasing from 55 categories to a little over 70. So there'll be more options for us to look at and categorize.
All right, let's thank our speaker one more time.